We're going to continue with fluids, right? So in the first section in 9.1, we talked about buoyancy. We talked about the properties of fluids being gases and liquids. In this section specifically, we're going to talk about pressure and depth. Very, very applicable. That's the reason I'm picking these two things to look at specifically here too. If you think about pressure and fluid pressure, it's everywhere. I was just literally loading these nozzles for the 3D printers. When that filament, that's plastic, gets melted, it gets put into a chamber called a chamber. It gets pushed out something called the nozzle. And that actual device over there suddenly was all backed up because it was a clog. So I cleared it and finally it started all pouring out. There was fluid pressure backed up. Yeah, I know, it's gross. It sounds like a pimple or something. Yes, I know. It's disgusting, right? But the concept of pressure is everywhere. You pump air in your tires, it's fluid pressure. There's water against the dam wall. So the Hoover Dam, the water is all up against the wall, right? That damn wall. No, the damn wall. So the Hoover Dam has all this water pushing up against it. That's fluid pressure against a retainment, it's called. You crack an egg. The reason an egg cracks when you hit it over the edge, concentrated pressure on that area causing it to break. Yeah.
When you go diving, you come up too fast and get air in your lungs because of the pressure imbalance.
Yeah, it's the pressure differential with depth. And we're going to see how that pressure is affected by depth. It's called the bends.
Yeah.
When the gas in your veins or the gas in your blood starts to bubble. Yeah, really, it does. And you could actually get very, very sick or die from it. It's called the bends when you come up from a depth of a certain amount too quickly when you're scuba diving. Ask Miss Moyler about scuba diving. She knows like all the physics of scuba diving. It's really cool. She took all these courses on it because she was interested in it.
And that could happen to you if you're in an airplane and you're going down.
Sure, absolutely. If you're too high of an elevation and you're dropping too quickly, the same thing can happen. But in that case, it would be the opposite, really. You'd be increasing pressure because you're moving down. Whereas when you're moving up from the bottom of the ocean, you're decreasing pressure.
Yeah, well, I mean, it still has a
Similar effect?
on your body, yeah.
Should you talk about the bends, the change in elevation or depth in the water? With planes was the statement, yeah, but with planes it'd be the opposite. As you get lower, you get higher pressure. Higher up is lower pressure, actually. Why is what? Is that the term when you descend? They call it decompression? I'm not sure why that's the term. At the highest point, it's definitely lower pressure because there's less air pushing down on you. That's why it's lower pressure. The air is thinner, higher up. That's what they said. Less pressure. Why would it be called decompression? Maybe the decompression of the actual cockpit and the actual place you're located in. If the window breaks, the air would flow out, not in. Because the pressure inside of an airplane is atmospheric pressure, the pressure that you're used to. The pressure outside the airplane when you're at a high elevation is low pressure. Air moves from high pressure to low pressure. That's called a pressure differential. So that's why you see when it breaks open in movies, people fly out and they get sucked out of the plane because the pressure inside is higher than outside. The air naturally flows out of the plane. So we're going to see how these are applied, okay? We're going to talk also about a really interesting and useful but a useful apparatus that was invented called a hydraulic lift. And a hydraulic lift uses the concept of differential pressure or pressure throughout a membrane or a fixed volume, the pressure in a fixed volume. I'm going to give you another opportunity for a little bit of extra credit if you want to do it for the next test with something as well. And I'll talk about it today as we go through it. Did anybody else do the one with the egg and the salt? Did you do it? I saw yours. Did you put it in your own folder?
Yeah.
Dropbox? Anyone else do it?
I saw it.
Try the next one then, because this was it was due yesterday for the test. Okay. Try the next one if you'd like to. Did you do it?
No, I was going to say that was already my idea for the egg drop.
Yes. Well, with the egg drop, you're looking at pressure with the egg drop as well. Absolutely. If you could equally distribute the pressure on the egg, it won't crack. And that's what we're going to talk about with this extra credit today. Let's begin the first. So the definition of pressure, the easiest way to think about this. How many, and it could be gentlemen or ladies, but traditionally ladies, how many of you have been in ballet or dancing at some point when you were younger? Usually girls do, and Tom. Awesome. So, Tom, can you get up and demonstrate for us? How about this? Yesterday at baseball practice, Tom was the best at this workout technique. What did Coach Robin call it? Did he get a name?
No, like hockey.
It's a hockey workout where you. What do? Do you want? Can you
Go.
do it? I'm sorry. Before you go, hold on. So, if I'm standing here, right? I'm just going to give you a little background before Tom demonstrates this, because this is a great example of pressure. If I'm standing here, my weight is applied over the area of the bottom of my shoes. Agreed?
Yes.
Like I'm literally contacting the floor with the bottom of my shoes. If I just do this suddenly, what happens?
Your balance.
My balance gets tougher
Yeah.
because the area I'm standing on decreases. And the area is clearly in this formula here. Tom's going to demonstrate a technique yesterday in baseball he did as like a workout to work on agility and stability. Those two things, really. The agility part is the motion. The stability is going to be the pause. So I try not to fall doing this. He was really, I know, it's really small.
So I'll just go like
Can
this.
you make it? Or yeah, try not to exaggerate. Yesterday we did a lot, yeah. So there's one guy. There's two. There's three. There's four. So this is the technique. Very good. Very good. In hockey you use to work on your balance. Because if you're skating in hockey, think about when you're skating. You're skating like this. So Tom is literally doing this, but holding it every time for that stability. What is he doing? He's increasing the pressure. That's what he's doing actually. Because look, he's standing normally like this, and then suddenly, you go left, and then right, right like that. Yeah. So he's just increasing his stability, or he's working on his stability by decreasing the area. By what factor is he increasing the pressure every time? So he's standing normally, and then suddenly goes to 1 foot. So now, what is the pressure compared to when he's standing normally, as opposed to when he's standing here?
What, double?
Double. Why?
Because it's one.
Because
Double
it's
the
mass.
pressure on 1 foot.
Yeah, because you're putting all the weight on 1 foot instead of 2 feet. We could see that pressure and area, how are they related? How are they related? Pressure and area. Thank you, Tom. How are pressure and area related? They're indirectly related, so you double the area or halve the area, you double the pressure or halve the pressure, depending on which one. So Tom halved the area, thus doubling the pressure acting on each of his feet. And that increases the strength in those supporting muscles in your legs. So anyone that does yoga knows there are a lot of yoga poses that are on one leg. A lot of them. So whether you're doing something like tree where you're holding yourself up or going down on 1 foot like this, doing any of these poses, you're putting a lot of stress on that one leg, which is increasing the stability in those stabilizer muscles in your legs. Obviously, if you increase the amount of force applied, you also increase the amount of pressure. Those are, how are they related? Directly. And that makes sense. That's common sense, right? You push harder on something, it's more force, more pressure. Chris, you do Taekwondo?
Yep.
When you break a wooden board, honestly, what's the contact like? Can you demonstrate? Not necessarily the punch, but the actual contact between your hand and the piece of wood. Where do you make contact in your hand and demonstrate the area you would point out? Yeah, like in a punch. Take a look at it, guys. First two knuckles. So, is it mainly up here or is it the entire surface area here?
It's kind of like the whole area, but you're really trying to focus on the
So, are these kind of extended in front a little bit, the other knuckles?
It's supposed to be flat.
Supposed to all 4 knuckles are flat, but you put the contact on these 2.
Yep.
Yeah, and that makes sense logically. Look, instead of punching like this with all 4 knuckles, where the force that I'm applying is displaced over a big area, if I only contact these 2 knuckles, I've decreased the area and thus increased the pressure. Increased pressure causes the wood to break, causes the person's nose to break, whatever it is that you're defending yourself against or practicing on wood. People, not wood, obviously. All right, so my units for force are newtons. My units for area is length times length, or meters squared. So my units are newtons per meter squared. PA, anyone? Pascals, very good. The French
That's a joke that was a thing where like the hide and seek.
Yes. Yes, that's right. You have it? You want to pull it up? Because it might actually be kind of funny now that we know what Pascal is. Can you just Google what it is to try and find it? Alright, try that. But the French mathematician Blaise Pascal was known for his work in a lot of scientific fields. He was a mathematician, yes. So Pascal's triangle is the same guy. But the unit of pressure we use for SI units is pascals. Anyone know what we use in the US or what we use in the English system? PSI for pressure, which stands for? Pounds per square inch. Anyone know other units of pressure, barometric pressure, anyone that that's measured in? It's an old school pressure that's not really used as much anymore. Millimeters of mercury was the measurement.
Wow. I got it.
Mercury used to be placed in this tube, and based on the air pressure that day, it would push down the mercury more, cause the mercury to rise. The mercury level that rose up was the amount of pressure in the air that day. It measured the pressure of the atmosphere that day.
The displacement was equivalent to the force.
Yeah, the proportional distance indicates how much applied force is down, which can be transferred into pressure using the area. Okay, this was using a, what is it called? A barometer. Barometer is a term that measures air pressure. Do you have it by any chance?
Yeah.
Is it actually funny still? Does it make sense based on this?
Yeah.
That's exactly what it is. How can I have Texas? Send it to me in an email real quick. So it's a really lame joke, but it actually makes sense when you look at it. So I'll put it up in a second. Before we get to that, let's look at the next slide. So for those complainers, how many of you in the room, raise your hand, be honest, are complainers? A couple of you are complainers, raise your hand if it is. Come on. Who knows complainers? Okay. Some people are not, so you like to complain. So here is a legitimate complaint. Okay, here's a legitimate complaint.
Too much atmospheric pressure.
Any fluid, remember, fluids are gases. Fluids are gases and liquids. Any fluid surrounding you applies a pressure on you. Because technically, if you think about it, if you're in the water in the pool, the water above you is pushing down on you. The weight of the water, literally above you, is pushing down on you. It's above you. It has to be pushing down on you. It's like a contact force. Any fluid that you're standing in or submerged in applies pressure on you. Right now you're submerged in a fluid. What fluid is that?
Oxygen.
Air, which is a composition of oxygen, nitrogen, argon, a few other things. Now, we call this atmospheric pressure. It's the pressure of the atmosphere from the air above you acting on you. This is why, as Chris said earlier, when you're in an airplane, there's less air above the airplane when you're up in the sky. So there's less pressure up there causing your ears to pop and that pressure differential. And your feet and anything like that to change with pressure. So here, this is the weight. This is the weight of the atmosphere. 1 times 10 to the 5th pascals. It's also known by another unit called atmospheres, ATMs. So if you have two atmospheres, that's 2 times 10 to the 5th pascals. 3 atmospheres would be 3 times 10 to the 5th pascals. So the unit of atmosphere is very useful because of the fact that everything on Earth experiences the pressure of the atmosphere in addition to whatever the pressure they're feeling. So for the complainers in the room, you could always say, there's a lot of pressure on you right now. I have a lot of pressure on you. I'm really stressed out in life. A lot of pressure acting on you.
When you're sick and you go on a plane, when it's landing, it's like the worst thing you can
Yes,
do.
absolutely, because the pressure is increasing.
Yeah,
So, when you're on a plane, I've been this way before. If you have a sinus headache or a cold on a plane, when you're taking off, it's great. Because everything suddenly opens up. You're like, there's no pressure. This is amazing. My nose cavities, they all start popping. You can start blowing your nose. Everything comes out. You're like, this is great. But then when you land, all that stuff that's in there starts to pressurize. And you start to feel this pain in your face. And you get headaches. It's the worst.
Yeah, this
The
lady,
worst.
I was like sitting away from my mom, and this lady like got up and she was like, "Pete, you're about to
Right?
Okay, stop crying."
It's a quick the greatest game.
Anybody get it?
Oh, I get it.
I've been listening to a lot. Yeah,
Because Pascal is the loser in the group, so they call him a square.
Nope.
It's a good system. I did that with Natalie on Sunday.
Isn't that what Newton drew on the ground?
Yes.
Okay. And then suddenly, what happened? He sees Newton sitting on the ground and he says, I found you. He found a Newton. He found a Newton per square meter though, didn't he? Was a Newton in the square meter? And what's Newton per meter squared? Pascal. Yeah, that was earlier. That was good. I like this.
Did he find Heisenberg?
No. Heisenberg cannot be found. It's uncertain if it can be found. You get that one or no?
No, not at all.
Heisenberg's uncertainty principle. Has to do with the position of electrons in a probability field. Look it up. It's cool. Quantum mechanics. All right.
Identity.
Oh, I learned. Oh, yeah? I've seen that. Steal your identity.
Did you see the joke I wrote on my text?
I have not looked at
Okay, this is a joke. Why did the dumb scientist? I thought it's myself, everybody. Why did the dumb scientist sink in the pool?
Because he was dense.
Yeah. It's so funny.
All right, so Pascal's principle says this, and this is what's the interesting part. That if there's pressure applied to a fluid that's in a closed container, and I'll explain what that means, then every point along the wall of that container feels the same amount of pressure. So if you've ever pumped up your tire of your bike, okay, so you're pumping up the tire, you're sitting there, you're pumping it up, right, and then you realize you feel the side of the tire, oh, it feels like there's a lot of air in there. If you feel any spot in the tire, does it change anywhere? No. It's the same pressure throughout every point in the tire. So the container is a closed container. It's a closed volume. It's a fixed volume. The pressure is distributed equally. Now, if there is a simple, small defect in the tire, and there's like a little tear, and the pressure is equally distributed, that pressure at that location, because of the tear, will overcome the actual strength of the tire, and the tear will spread. That's why if you pop a tire, it happens at one location. There's a fracture point, or not a fracture point, but a failure point. That failure point is the exact same thing as like taking an egg and cracking it over the side of the dish. You never take an egg and try to open the egg by holding it like this, do you? You take the egg by doing this.
Because I hard-boiled eggs a lot, and so I tried to crack it, just like switching it with my hands, and it
The whole thing probably squished, right?
yeah, the whole thing.
Yeah.
Just like,
You lightly tap it to crack one corner. Now, here's your extra credit. Ready? So, take an egg. I'm going to try to demonstrate what an egg looks like with something that's...
I have a tennis ball.
I need it to be like a blade.
Oh.
So here's an egg, okay? I know it's not an egg. Here's an egg. So take the egg the long way like this. Okay? Take that egg, place it in your hand.
wait, are we passing?
Yeah, it's what you're doing for extra credit. Okay? You're taking the egg, you're placing it in your hand. Now, listen, please. You want to get your hand completely around the egg. This is not a good example because this cylinder is bigger than an egg would be. But imagine the egg is in my hand. I want to technically close my hand around the egg. So I'm holding the egg now. It's in my hand, okay? The egg's in my hand. I'm not holding the egg like this, or like this, but like this. Please listen first, let me get this. You hold the egg. Now, try to crush the egg by squeezing it, but equally distributing your squeeze. And this is not easy to do. If you squeeze too much with one finger, it will crack right on that finger. But, and you'll see it, and you can see it, the way I'll be able to see in the video is I want you to video record your arm. You can literally see your arm like bulging when you're squeezing. Okay, squeeze this egg equally around the whole outside. And because of Pascal's principle, that pressure that you're distributing, because you're distributing the pressure equally, will be reacted equally amongst the surface. The egg will not crack. It will not crack, I'm telling you now. Okay, you can squeeze it as hard as you want. As hard as you want, you can squeeze it. As long as you're equally distributing the force that you're applying to the surface of the egg. So you kind of have to like contour your hand around the egg and squeeze all at the same time equally. You squeeze too much with one finger though, or if you slip, or if your nail hits it or something like that, it may crack. So please do this over a sink. Please don't just do it randomly at home and then get it everywhere. Put it over sink, just in case it breaks. Now, please record yourself doing this so I can see that you're actually squeezing. I don't want you to be like, oh, I'm squeezing, like you're faking it clearly. I should see your arm like, bulging when you're squeezing it. Okay, but try it yourself. Try it yourself and have someone record you. Nick, you had a question?
Yeah, the egg project, can we have a human vessel and just have somebody holding?
No. Alright. Next. I'll make it yourself, Nick. If you can figure out a way to make it yourself, I'll if you're going to talk about a human, you got to be able to sacrifice yourself, right?
I was thinking of making a rocket ship because if it goes up, it has to come back down.
You can do anything that is less than $10, that doesn't abide by those, or doesn't break those other rules.
Can it
It
be
doesn't have electronic stuff. No electronic. Remind me when we're done with this lesson in the second period. I'm going to have something else we're doing. I have it on my calendar. I'll tell you the due date when we're going to test the egg dry. I'll put it on the little shirt. Yeah. All right. Now, here's what's cool. We can take this concept of Pascal's principle, where the pressure is distributed equally to any location of the container, and we can apply it to what's called a hydraulic lift. Now, many of you have actually used this before. If you've ever been to the hospital for any surgery, and the bed is able to lift and lower on a little device on the side, it uses a hydraulic press. If you've ever been in the car before, when you hit a speed bump and the car dampens off real quick, it doesn't do this forever, it's because the pistons have hydraulic fluid that prevent motion with what's called a viscous fluid motion, or viscous force. Take your hand in the pool and do this. The faster you do this, the more the force will be, because the viscous force is proportional to the velocity. Give me 1 sec, both of you, I know. So here, we're going to see that if we apply a force on one end, that force gets magnified on the other end. This is what's called a mechanical advantage, like a lever or a pulley. Pulleys, levers, screws, these are all things that apply mechanical advantages. Inclined planes, they're all mechanical advantages. This is another example of that because of Pascal's principle. Okay, I'm going to show you how that works real quick mathematically. I promise I'll go back to you guys. Just please remember what you're going to say. So we know the following. Since the pressure at any location has to be the same, that's Pascal's principle. That means that the pressure here and here is the same. So start by writing P1 equals P2. This is capital P. If you want to make it a capital P, some people like to do this. You can. Like we did that for V to indicate capital. It's not lowercase, it's not rho, right? It's not density, rho. It's not lowercase p, it's capital P. Lowercase p is momentum. Capital P could be power or pressure. Either one. You have to know which one it is based on the context of the formula. Pressure equals F over A. Replace it. Now, mathematically, please make sense of this. Look at the diagram on the right. Where the force is applied at F1, is that a bigger or smaller area? Where the force is applied at F1, it's a smaller area. It's obvious by looking, but it's not. There's no number there, okay? So, we pick a number that's smaller, or a small number for A1, hypothetically. Okay, pick a number that's smaller than A2. Maybe let's make A1 half of A2. Just
2 and 4.
So 2 and 4? Okay. So this becomes 2 and this is 4. That works. I'm going to use numbers to prove this, and then we'll talk about it mathematically to see the direct and indirect variation here. Now, how much force are you going to apply? Give me a number in newtons. 5 newtons of force. Do we know, by the way, number sense, what 5 newtons of force is?
No.
What is a newton compared to a pound? Anyone know? Google converter real quick. We did dimensional analysis earlier in the year with this. Right? Please Google it. 1 newton to pounds. How many pounds is a newton? 1 newton to pounds. Because I know a pound is, or a kilogram is 2.2 pounds. I know that much. Yeah, it's about a fifth. Good. About a fifth of a pound is a newton. So when you say 5 newtons, you're telling me that you're applying 1 pound of force. That's fine. We'll use that as our number. But just so you know what you're saying, okay? So you apply 5 newtons of force over 2 square meters. The other side is a piston with a cross-section of 4 square meters in area. Well, what's the force that's going to be felt by the car? Chris? 10. The missing number is definitely 10, because 10 over 4 is 5 over 2. Would you all agree?
Yes.
So, this tells me that, what's my mechanical advantage? From 5 to I put in 5, but I get 10 out. My mechanical advantage is 2. How do you get that? It's a, what's the term for that? Factor of increase. Factor of increase.
How neat is that?
That's the mechanical advantage. Well, why did that happen? Why did that happen? Sam?
So as the pressure went up, the stability also went up, you increase the stability by
Not stability. I need more than that. You definitely increase the force that you're going to feel by a factor of 2, but I'm asking why. Why did this go up by a factor of 2? Why is that?
Is it because of the direct relationship between the forces and the force applied and like,
Caroline?
is it because I mean, you're asking why.
I'm asking why this increased by a factor of 2.
Because the first fraction has to be proportional to the second fraction.
Correct. So give me physically why.
Because the particles of the like
It's more obvious. I think you're all thinking too hard. Chris? No, you can't lose pressure here. The pressure is equal throughout all. So
2
the
times
pressure is
4 and 5 times 2 is 10.
Thank you. Only because, you double the area, you double the pressure. I meant physically why. That's why I was asking. Okay, the proportionality of the fraction is what's important, obviously. You're doubling the area applied. So you have to double the force to get the same pressure. And since the pressure is the same throughout any hydraulic, it's called a hydraulic lift. And a hydraulic lift is the same pressure throughout. So if I double that area suddenly from one end to the other, I'm doubling the force. I have to be. So my mechanical advantage, jot this down please. My mechanical advantage is equal to the factor of increase of area. The area doubled here. The force felt by the car lifting it up was double what you put in. So the mechanical advantage, as Caroline said, was 2. That's also just the factor of increase. That's also just the factor of increase for your area of the actual piston. The area doubles, so the force itself doubles. Is that clear? Okay, mechanical advantage comes from the change in area, really. That's where it comes from. The contact area. Yes?
Have you ever seen the YouTube channel, the hydraulic press channel?
I have not. Do they just put stuff in a hydraulic press and crush it?
It's just this Finnish guy who just crushes random crap.
That's really cool, actually. You know what? I'm talking about that in engineering right now. I'll show that tomorrow. Thank you. Because in engineering, we're talking about what are called tensile tests and compression tests with certain specimens to measure their strength. Concrete, steel, how it like starts the neck and stuff and gets plastic. So it's called, what is it called?
Hydraulic press channel.
Hydraulic press. Okay, cool. I'll look it up because there's probably some fun stuff on there, right?
Yeah.
So you were talking about like pressure with fluids and like how if you press harder on water it like resists more. I was watching this video where the guy shot a gun into like cornstarch and water, so it comes like roulette. But like when you shoot, like when he shot like a balloon full of it, like it fell like a solid, and then all of a sudden it turned.
So the stuff that she's talking about is called oobleck. That's what we're doing. It's a non-Newtonian fluid. And non-Newtonian fluids under what is called high impact or high impulse behave like solids. You could literally, it's a fluid, you could put your hand in it slowly and your hand will go in and come out. But if you punched the fluid, it would act like a wall. It's the coolest stuff ever. So at my last school in DC, we spent 3 days making a giant vat of this stuff. And we literally made the vat like this long. Took off our shoes, and you could run across the surface. If you did it quick enough, it was like right off the surface. But if you stood at any point in time, you'd sink right in. It's called oobleck is the name of it. You just take
We tried to make that
cornstarch and water. Last year.
We made it, but we just played with it. We didn't really do anything.
We didn't ever do anything crazy.
That's what me and Gabe are doing for exercise. We have a container.
Somebody else
Oh.
did it with a concrete mixer on, what's the show? It might have been like, not How It's Made, but Mythbusters or one of those. They took a concrete mixer and they just put a ton of cornstarch and water, filled like a pool with this stuff. And the person was literally like running across the surface, and then he would stop and just start sinking in. It's very cool stuff. It has to do with impulse. Higher impulse, it acts like a solid. The actual the surface tension increases dramatically because it's a non-Newtonian fluid. That's why that happens. Caroline, go ahead.
Yeah, and there was like I think it might be the same episode that you're talking about, but like they wanted to see like if you already sunk in, if you could step out of it because you're applying pressure through the middle of it.
Were you able to or not? Yeah. So that's kind of cool. If you're in the bottom, imagine that in the middle, you just suddenly like push really hard. That would become like a solid, like a step would appear in the fluid. Steps would appear if you push really hard, because pushing hard is high impulse.
But you can only press down because if you press up, then your knee gets stuck in the wall and you get.
Oh, true. If you go like this really quick,
Yeah.
your knee would hit a wall on the way up. Technically, the fluid
Yeah.
would turn into a solid. So you like push down hard, and you like slowly. That's cool.
Oh, that's cool.
It's very cool.
That's so scary.
All right, let's go to the next slide, please. Example. Your answer is very quick.
You just go up.
Okay. So we got a hydraulic lift. You apply 550 newtons of force on one end of it, on a small piston, to support the weight on the other end. How much weight can actually be supported? And then what is the actual pressure on each piston? So use the equation from the previous slide. F1 over A1 equals F2 over A2. Whenever it's a hydraulic lift, you go right to that formula. F1 over A1 equals F2 over A2. You have the areas in this problem. If I gave you diameter, what should you do? Calculate the area. If I give you radius, what should you do? Calculate the area. If I give you area, you just plug that right into the formula.
Calculate the area.
No. Plug it right into the formula. Okay, simple math. Force applied over area applied equals force felt over the area of the second part. Solve for F2. Move the 4 over. Take a look. Ready? Watch. Just to prove this again. Multiply by 4. They cancel. Multiply by 4. Well, here's the ratio of increase of the area right there. 4 over 1.5. That's the factor of increase, really. Again, this is the formula. I have a 4 here. Multiply by 4 on both sides. This, what I circled, is your mechanical advantage. This is the mechanical advantage right here. What's the answer? What's the answer again?
1,466.6.
Okay? So this goes up by a factor of 4 over 1.5 or 8/3. Look at the 4 over 1.5. Isn't that really 8/3?
Yeah.
If I double both the top and the bottom. Right? Double this makes it 8. Double this makes it 3. So the mechanical advantage here is 8/3. Do me a favor. Type in 8 divided by 3. What's your decimal? Or do you know it? I don't want to assume. What's 8/3? Anyone knows the decimal? Yeah, 2.6 repeating. Take 1466 divided by 550. You will get 2.6 repeating. That's what the mechanical advantage is. It's by how much does the force felt increase, by what factor. So it's amazing to think about this. I could sit here and only apply 550 newtons of force, yet on the other end of that press, it's feeling almost 1,500 newtons of force. Very, very useful. It's the same as a lever. That's how a lever works with torque. If I double the lever arm, I get double the torque. When we did this with torque, remember how this worked? It was a mechanical advantage. You take a torque wrench, you can just take a sleeve, add it to another wrench, and suddenly you're applying a force over a lever. If you had like a big lever and you push on the end of it, you get a lot more torque out of a small little lever that you're pushing on. Same thing with mechanical advantage.
Isn't this how they use brakes on roller coasters?
It's probably a hydraulic press. It's usually hydraulic fluids in the braking system. Most braking systems, almost all braking systems, are hydraulic fluids. There was a really cool video. It was a live thing that Ford did on Monday at noon. They did this thing where they looked at like new generation cars. And I was going to show it in my engineering class, but I didn't meet at noon. So I could look at the archive of the video. I got to find it though. They haven't put it up yet. But they talk about hydraulic brake systems for a while. And when you go to get your brakes fixed, you get your brakes tuned up, you replace one of two things. The brake pad, which contacts the actual tire, which eventually like disintegrates, it rubs off, it's with friction. Or you get your brake fluid replaced. Your brake fluid is what allows hydraulic presses to work. It pushes on one end, which pushes the brake pad against the actual wheel well, which slows it down. But it's using Pascal's principle by transferring that pressure from one end of a piston to the other with a different area. The different area gives you a different amount of force being applied.
The brake pad in the car is probably the same thing on a bike, right? Because it has
It's analogous to that.
squeeze.
Yeah. But a bike does not use hydraulic pressure. A bike uses a spring, and when you pull on the spring, there's a little cord in there that like tightens the tension or loosens the tension, and the bike pulls, which causes it to move. But a brake on the car, you push the brake with very little force. That force gets magnified by a factor of like 100, and the fluid that's connecting it to the brake pad gets pushed with a lot more force than actually what you're pushing down with.
So you shouldn't use hydraulic brakes on
I mean, you wouldn't need them really. You don't need them. They're not
really
necessary.
fast.
Maybe a motorcycle.
I was on a plane that was ready for takeoff, and then the captain said on the intercom that the brake pads weren't working. So luckily they caught that before we took off.
Yeah, because landing would be the problem. But keep in mind when you're landing, what provides most of the resistance really?
Your wing.
The wings, the flaps raise up. Provides a lot more air resistance. But there is also brakes on the actual wheels themselves. Chris?
I got two things.
Yeah, go.
There's also, it's what I said, the whole reverse thrust thing.
They what?
There's reverse thrust on the plane, so like, there's a section of that engine that kind of slides out, so instead of thrust pushing back,
It pushes forward.
yeah.
That makes sense. That's like blowing air, moving yourself back on like a
And
well, hold on, one more. You said two things you said. Hold on a
I
second.
was gonna say,
Sorry.
like, when I was younger, I was really disciplined, so I know that planes also work with they used to have these hydraulic control surfaces. So you move the stick in one direction and moves the whole, there's like hydraulic lines going throughout the entire.
Oh, absolutely. And the force you apply on that is much less than what's being applied on the actual mechanism. Think about it. You change the angle, suddenly the flaps are adjusting, right? Well, the force needed to adjust the flap under air pressure that you're flying through is much greater than what you're actually pulling down on the handle with. Your steering wheel has what's called steering fluid, power steering fluid. Has anyone's parents ever complained about the steering fluid being out? It's almost impossible to turn the wheel. You guys haven't really, well, some of you are probably driving now or taking lessons at least. When you turn a car, it's very easy to turn the wheels. That is not really what's happening. The force you apply gets magnified by the steering fluid. The steering fluid, the pressure involved, allows those wheels to turn. Because the wheels contacting the ground are under a ton of friction. So if you actually tried to turn the wheel and turn those wheels on the ground, they'd be like making noises and stuff. You'd be barely able to turn. You'd be trying to really turn hard. But the steering fluid is what makes it a lot easier because of this mechanical advantage. These are great, great examples you guys are adding here. Okay? This is the kind of stuff that I like to talk about because it's real, it's actually applied. Last talk about this theory and then we'll do an example of it. Pressure variable with depth. And you know this, we talked about it, Caroline already talked about fluid pressure as you get lower and lower and lower. When you're scuba diving, you can't come up too quick because the pressure changes too quick. So here's how we think about this. Think about this just like you think about atmospheric pressure pushing down on you. But when you're under the water, you've got water pressure down on you and the atmosphere pushing down on you. So let's derive this formula for a second. Let's start with pressure. Pressure equals F over A. Force over area. The force that's being pushed down on you when you're underwater is technically the weight of the water above you. If you could extend a column of water directly above you, it's almost impossible to see this. I'll take a look at an example with a box. Draw yourself a box, please. Because with a human, it's way too hard to draw this. Humans, petty humans. So there's the water level. This box is on the floor. Okay, now, if you think about this, Imagine a bird's eye view. Stop. Whoever's out there is distracting a lot of you. All keep looking. Stop. Think about, there's people outside that keep distracting. Everybody keeps looking out the door. This box under the water, imagine if you look down at it from above. What shape would you see?
Not a box.
If you look from directly above a box, what shape?
Square.
Or
A rectangle.
good. Some rectangle. It could be a square. We don't know. Now, if you take, please listen. If you take that cross section that you see and extend it vertically upward. Look at me, please. Look. You take the square or the rectangle you see and extend that vertically upward until you get to the top of the water. It would be literally a rectangular prism that comes straight up from these four corners. And this would be like a column of water that's weighing down on you. Do you see what I'm saying now? That's the weight I'm specifying here. The weight of that water is the pressure that that box is feeling, or the force that's giving the pressure. So, we're going to replace force with weight. So we call it Fg. But Fg equals mg. This is like the first formula of the year, or one of them, come on. So, why am I putting F for? Fluid. Now, remember please that mass equals density times volume. Where does that come from? Here. Density is mass over volume, so mass is density times volume. So replace mass with density times volume. So the pressure is the density of the fluid times the volume of the fluid. Now, before I go any further, what is capital A? What area?
The area of section.
Yeah, very good. When you look down at that box, the area on the top of the box, that's A. Okay, that's A. Now, this is a little bit of heavy math for you to do here. You learn this in geometry, whether you realize it or not. If I were to look at this, and I wanted to know the volume of a rectangular solid, I know it's LWH, length times width times height. Are you with me still?
Yes.
So I can replace this volume, VF, this is the volume of that channel of water above, with LWH. But what's LW?
Area. Oh, so you can cancel it.
It's the area right here. This is really, again, replace this with LWH, but LW is area. So LW cancels with area, leaving behind rho GH, or rho HG, it doesn't matter. It's traditionally written as rho GH though. That's the derivation of where this is going to come from, so you know. So if you want to know the pressure acting on an object, it turns out that the area doesn't even matter. The area canceled. Look at the previous line here. The area canceled. So if I take this object and this object, and I put them both underwater at the same height, H really is depth, by the way. Wrote a note. H is really the depth in the water. It's the height of the water, right? H is the height of the water acting on this object, which is depth, because it's underneath the water. So H is the height of the water pushing down on this object, which is really depth. So these two objects, if they're at the same depth, feel the same pressure. It's not a function of the object itself, it's a function of only the fluid, density, rho F, and the depth in the fluid. G is a constant on Earth, so it's not a function of that. Okay, so the pressure felt underneath the fluid is this number. Now, that's the pressure from the water that's in that column above you. But what's above water? Air. So technically, we do this. Ready? We call this gauge pressure. I'm going to spell it right. This is called gauge pressure. There's also something called total pressure. And total pressure, there's no different subscript, by the way. It's written like this. It's rho GH or rho HG, it doesn't matter. What is the P0 again? Anyone remember?
Object.
I know, you think it's object, it's always object. I talked about this like 2 slides ago.
Oxygen.
It's the atmosphere. Think about it, ready? If you're underwater, the water's pushing down on you, but isn't the atmosphere pushing down on the water?
So it's the pressure in the atmosphere.
So it's the sum of those two. This is atmospheric pressure, PO. Write a little note, please. Next to PO is capital P. PO is atmospheric pressure. It's literally the weight of the atmosphere. Rho GH or rho HG is the gauge pressure, which is the pressure of the water. So if you want to write this out, you can write it out so you're clear about this. So total pressure equals atmospheric pressure plus gauge pressure. The total pressure felt is always atmospheric plus gauge. So if a problem were to ask you about gauge pressure, all you got to do is rho GH or rho HG. But if I ask you the total pressure, or I say find the pressure acting on an object underwater, it's assuming you're talking about total pressure. Gauge pressure is just the pressure inside of the fluid. So in a bike, when you're pumping your bike or you're pumping up your tires of your car, and you put a little gauge on there, a pressure gauge, to measure the pressure, you're measuring the gauge pressure. It's the pressure inside of the actual tire. Okay, inside the actual tire. Not including the atmosphere acting on it. All right, look at this last thing. Calculate the depth in the ocean at which the pressure, now this means total pressure if you don't hear anything else, doesn't say gauge. Calculate the depth in the ocean at which the total pressure, even though it just says pressure, the total pressure is triple or 3 times the atmospheric pressure.
So we're solving for H.
Okay, calculate the depth, which is H. Very good, Sophia, right away. She thinks, oh, we're solving for H because it says depth. That's unknown. The density of salt water, 1025. Atmospheric pressure is a constant. It's on your formula sheet. It's at the very bottom. This is what we wrote down maybe like 3 or 4 slides ago. 1 times 10 to the 5th pascals. That's atmospheric pressure. It's also known as 1 atmosphere. Okay, but because we're using units of kilograms per cubic meter and newtons, we're going to put everything in pascals here. So, here's my formula. I'm simplifying. In the formula, I don't put F for fluid. You should know that there's an F here next to rho. Again, there's no F right here as a subscript, but it's the fluid. So here's my formula. But the question said, find the depth. So right away we know we're looking for H. So this is what we're trying to isolate. We know density is given. Gravity is on Earth. P0 is given. It's a constant. What is the total pressure though?
3 times the atmospheric.
It's triple atmospheric. That's what it said. The problem said, find the depth so the pressure is triple atmospheric. So replace pressure with triple atmospheric pressure. And that's what your formula now becomes. And now you have like terms. You can move the P0 over, 3P0, subtract 1P0 from it. Again, it's triple atmospheric, so I put 3 P0s. Subtract P0, subtract P0. Gives us 2 P0. Equals rho GH. Get H by itself by dividing by rho G. So that's H. 2 P0 over rho G. And you have all the information. P0 is a constant. G is a constant. The density of salt water is a constant. These are all constant values. You don't have to vary them. So I'm going to plug them in just so you can all see this. You've got 2 times atmospheric pressure all over the density times gravity. Okay? You're going to get a depth of 19.9 meters. 19.9 meters. Now, negative, positive, I really don't care for this kind of stuff because you know that it's going to be below the water level. We're looking at depth. Okay, depth. Any questions on this? Any questions? a lengthy answer to a bit of a complicated derivation that we started with, but something that's not unreasonable to ask. Okay? So we have really two concepts from this section: hydraulic lifts with pressure and pressure as a function of depth in a fluid. Those two things really. Okay? But we should understand the concept of pressure and how pressure is the force you apply over an area. That's why a pin can break a balloon. Raise your hand real quick. Siobhan, you were there. Was anyone else at the physics show?
Oh, yeah.
3, 4, 4 of you. Yeah. Oh, wow. I forgot. All 4 of you in the room. Perfect. The other class, there's only 1. So the 4 of you were there. Do you remember what demonstrated this?
Oh,
The balloon?
The hum,
The bed of nails. Good. There was a balloon. This guy did this. It was actually really cool. He took a balloon. And he took the balloon, and he took a bed of nails, and there was a nail like every centimeter. So imagine a lot of like actual nails, like sharp nails. He took an apple and threw it at the nails, and it sliced right in to show you how sharp. He took a balloon, and imagine a lot of nails right next to each other, and he smashed the nails with the balloon. It wouldn't pop. Because the force you're applying is over all those little areas, so it's a very low pressure. Then you take a pin, and you go like this to a balloon, it pops right away. A pin has very little surface area, so the force you apply, it creates a lot of pressure. Because there's remember, area and pressure are inversely related. So the more nails, the less pressure you feel. So then what did he do? He laid down on the bed of nails, put another bed of nails on top of it, and had a little girl stand on top. Nothing happened to the guy at all. Because there were so many nails, which displaced her weight over his whole body instead of over one nail. You put one nail, you ever step on a nail before? And it'll go right through your foot.
Oh.
Okay? You step on a bed of nails, you can literally walk right across. Don't try this at home. Want to be risky, be careful. But your extra credit is not walking across a bed of nails, it is the A.
What if they're
Unbreakable
rusty
A.
nails?
What?
Would you get more credit if they're rusty nails?
If they're rusty nails?
Yeah, if you get tetanus.
Alright, that's